relative velocity method, right? So we studied like two methods. One is instantaneous center method to find the velocity, and the other one is relative velocity method. This one is relative velocity method, right? So we'll see what is relative velocity is, right? Say for example, you have two bodies, right? So two bodies are moving with velocity A and velocity B, right? So this is the body A, and this is body B. They are moving with velocities VA and VB in parallel lines, okay? First we'll see for parallel and then we'll see for unparalleled movement. So when these two bodies are moving, right, we need to know how much is the relative velocity between them. So how do we find them? Say for example, we have this velocity of A is 50 meter per second and velocity of B is, say for example, 100 meter per second. Okay. We need to find now the relative velocity between these two bodies. In order to find that, what we will do is we will give the velocity which is equal either to this or to this, relative to which we are going to find the relative velocity. So, say for example, now this is moving with velocity of 50 meter per second this way, right? I will give another velocity, the exact opposite direction, which is again 50 meter per second, right? So when I give this velocity opposite to the direction which I already have, what will happen? This VA is this side 50 meter per second, and now I am applying another velocity which is that way 50 meter per second. So altogether, the resultant velocity of this body is 0, right? 0 meter per second, right? So now what I have done is I have stopped this body from movement, right? Now this body is not moving, all right? Similar way, I will do for this also. So since I have applied 50 meter per second here, I will apply the same 50 meter per second here for this body also, right? So when I apply 50 meter per second this way to this body, and this body is already moving in this direction 50 meter per second, sorry, not 50, 100 meter per second. Now the resultant velocity of these two is equal to 50 meter per second this way, right? Because this way is coming with 100 meter per second. I am applying 50 meter per second this way, right? So resultant is 50 meter per second, right? Now I can say velocity of B relative to A is equal to 50 meter per second, right? Velocity of B relative to A is equal to 50 meter per second. So if two bodies are moving, right? If two bodies are moving, I will stop one body, right? I will stop one body, and relative to that body, I will see the velocity of the other body, right? So I will stop VA, and then I can see the velocity of B relative to VA, right? I can do the same for the opposite way also, right? So say for example, the similar case, right? The velocities and everything is same, right? So now I'm going to see the velocity of A relative to B, right? So relative to whatever the body which we are going to see, we will stop that body. All right. So now I am going to see the velocity of A relative to this body B. So now what I have to do, I will stop B, right? So if I want to stop B, I will apply 100 meter per second this way, right? This is already moving this way with 100 meter per second, right? I am applying another velocity this way to stop this body, right? So if this way is also 100 meter per second and that way is also 100 meter per second, the resultant is 0, right? So now I have stopped the body B, right? I now stop the body B. Now I am going to see how much is the velocity of A with respect to B, right? So since I have stopped this by applying 100 meter per second to B, I am going to do the same for A also. I am going to apply 100 meter per second here, right? To A. So now the resultant of A is dA this way 50 meter per second, right? And now I am applying a force, not force, velocity, that is 100 meter per second this way. So now the resultant is 50 meter per second this way, right? So the velocity of A relative to B is 50 meter per second this way. Velocity of A with respect to B is equal to 50 meter per second this way. Or else I can say 50 meter per second this way, but with the sign minus, right? This is how we find the relative velocity of two bodies moving parallelly, right? Moving parallelly. You know, parallel means these two will never meet at any point, right? These two will never meet at any point. Those two will go parallel to each other, right? So if I take this as like find write it in the equation, right? So you understand this concept, right? Now we will put it in the equation, all right? Now I am putting the equation. So I will mark few points. O, A, right? OAB. All right. So now, if I want this system, right? What I will do? OA, right? I'll write it like. Now we will put in the equation. Right? So I will erase this 50, 100 and everything. Now we will slowly move to the concept, right? Right. So A body moving with BA, right? B body moving with BB, right? So BA, right? BA equal to OA minus OB, right? BA, right? This BA will be equal to OA minus OB, right? So this distance is this distance minus this distance. All right. So this is how we find the relative velocity of two bodies moving parallel to each other, right? So other way also you can write, right? So relative velocity will be written as velocity of body relative to the other body, right? Velocity of the body which we are looking at relative to the other body, right? So velocity of A relative to B. All right. So this is for the body moving parallel to each other, right? Parallel to each other. Now we'll see if the bodies are not moving parallelly, if they are moving in some angle, right? So these are moving parallelly. Now we are going to see if the bodies which are not moving parallelly and if they are moving in an angle. Right? Say for example, I have two bodies. A is moving this way, right? And I will take my direction B. Okay. And this is BA and this is BB. Alright. Now how are we going to form? So you know, if two bodies are not moving parallel to each other, those two will meet at a point, right? So this and this are not parallel, so somehow they are going to meet at a point. Alright. So I will extend. So somewhere here they will be meeting, right? So now we'll see how to find that. Right? So again, the concept is same, right? A is moving this way with velocity VA. B is moving this way with velocity VB, right? Now we need to find the velocity of either A relative to B or B relative to A, right? We'll write this as how to do that? say I'm going to find the velocity of A relative to B, which means I'm going to stop this V, right? So how I'm going to stop this V? Since this is moving with BB this way, right? I'm going to apply a velocity on the other way, right? So I will apply BB this way, right? So then, similar way, this BB I have to apply to this body also, right? Then only I can stop this body. Not stop until I can find. So in this particular angle, I'm going to apply a velocity BB, right? For A also, right? Here also I am applying BB to stop this. Same BB I am applying here also, right? So now this BB is stopped. This is not moving, right? BB is stopped. This is not moving anyway. Now I have a velocity VA this way, and now applied another velocity this way, right? So the resultant of these two would be something like this, right? You know, right? Moving this way. Now I applied another velocity this way, right? And the resultant would be connection of these two lines, right? So this is this VAB, right? So here we found the relative velocity of A with respect to B, right? VAB, right? So this is how we find the relative velocity of two bodies moving in unparallel direction, right? They are not parallel; they are moving in a kind of inclined direction, right? VA is equal to, formula is again same, right? So if I want to find the relative velocity, either VA minus VB, I will go for O VB minus VA, right? So for both these things, the magnitude is going to be same, but the direction would be probably different, right? Minus would be gone. Right? So with this brief introduction, we will go how to find the relative velocity in mechanism. How to find the relative velocity in mechanism. So mechanisms, you know, this 4-bar mechanism, cytochrome mechanism, quick return mechanism, we have several mechanisms. And we know that relative to a point, right, we can find the velocity of any arbitrary point on a mechanism, right? So we'll see how to do that, right? So now, motion of a link, right? So say for example, I have a link, okay? Say for example, this is a link, all right? Motion of a link. Say for example, I have a body, right? This is the body, which has 2 points A and B, okay? The relative velocity of B with respect to A, right? Relative velocity of B with respect to A is represented by the vector AB, right? Here we have the vector AB and is perpendicular to the link AB as shown in this figure, right? So I told you, if we are going to talk about a link, right, the velocity of the link would be perpendicular to the link, right? So if AB is the link, then the velocity of AB would be perpendicular to the link AB, right? So now this is moving with an angular velocity omega. Omega is angular velocity of link AB about A. So this is A about this particular point. This is moving the angular velocity omega. We know that the velocity of the point B with respect to A is equal to VAB, right? Sorry, VBA, right? Velocity of the point B with respect to A is VBA, right? VBA. So this is the velocity of point B with respect to point A. So that is given by this length AB and direction, right? So here direction and length are important things, right? So VBA is this side, this direction, and this direction, right? That is equal to AB bar, right? Since this is vector quantity, we use this direction vector. So AB bar. So AB bar is equal to omega into AB. We know velocity is equal to R omega, R is radius. So if this is rotating about this point, this is the R and this is the omega, right? This is the omega. So omega into r will give you the velocity. So VBA is equal to omega into AB, right? Similarly, the velocity of any point C on the AB, right? So this is C, any arbitrary point, right? This is any arbitrary point. So velocity of this C with respect to A is this side VCA, right? VCA. So VCA is equal to length AC into angular velocity omega. That is omega into AC, right? Omega into AC. From these two equations, we can go for a general equation to find the arbitrary velocities, right? From equation 1 and 2, VCA by VBA, right? So equation 2 divided by equation 1, VCA by VBA equal to AC bar upon AB bar, right? AC bar upon AB bar equal to omega AC upon omega AB, right? Omega AC upon omega AB. So this omega and this omega will be removed, right? Which would be equal to AC upon AB, right? AC upon AB. So by magnitude of the lines what you are drawing, we can find the velocity, right? So the ratio of the lines, right? Ratio of the length of the line is going to be the factor, right? This is going to be the factor which will decide the velocity of the body. So when you are doing this numericals in this section, right? We need to look for the magnitude of what we are doing, right? So if a question is given, right, and if we are going to draw a picture for that question, right, we need to consider on the magnitude also, right? So that is, you need to go for a scale factor, right? Say for example, if it is given like a crank is rotating with some omega 100 rpm, is of length say like 1 meter, then you need to go for a scale factor. So how are you going to denote this 1 meter in your copy or exam paper, right? So say for example, you take 1 meter as 10 centimeter, then the scale factor is 1 is to 10, and you need to follow this scale factor throughout this drawing part, right? Because by measuring your distances and lengths, you are going to find the velocity. That's the important factor here, right? You see here the ratio of VCA upon VBA, that is velocity of A with C with respect to A and velocity of B with respect to A. This is velocity, right? This is velocity. And if you see here, AC and AB, they are lengths, right? So the length will give you the velocities, right? Lengths are going to give you the velocities, and you are going to measure the length in order to find the answer, right? So here we need to mark this length according to a scale factor, right? So when I do a numerical, you will understand how it is going to impact, right? Right. Then we have rubbing velocity at a pin joint, right? What is this rubbing velocity is? So rubbing velocity, you know, if there's a pin, right? If there's a pin, then the pin, there are two links, right? So two links are going to the pin. So for example, like I have two links here, right? And they two are pinched by a pin, right? So when this is rotating, right? When this is rotating, okay, there is some kind of friction in the pin, right? There would be some kind of friction, right? So rubbing velocity at a pin joint, the links in a mechanism are mostly connected by means of pin joints, right? So if you take a linkage, right? If you take a linkage, that is mostly connected by pin joints. Rubbing velocity is defined as the algebraic sum between the angular velocities of the two links which are connected by pin joints multiplied by the radius of the pin, right? So, say for example, I have this link, right? I have this link, and both are rotating with some angular velocities, right? So, now how to find the rubbing velocity is the algebraic sum of these angular velocities, right? If only this is moving, or only this is moving, or whether both are moving, doesn't matter. algebraic sum of, so sum between the angular velocities of the two links which are connected by pin joints multiplied by the radius of the pin, right? So you might have studied this Gajan pin and all, right? So the pin might have some radius, okay? So that radius multiplied by the angular velocities algebraic sum. When the pin connects one sliding member and other turning member, the angular velocity of the sliding member is 0, right? So say for example, I have two links. This is one link and this is one link, okay? And they are connected by a pin here. And if this is moving with some angular velocity, if I have this as A and this as B, this is moving with omega A and this is moving with omega B, okay? And the radius of this pin is R, right? Radius of this pin is R, okay? So algebraic sum means if this is also moving, this is also moving, we will have either omega A plus or minus omega B, right? So I will say what is plus and what is minus, right? Into this radius, pin radius R, right? When the pin connects one sliding member and the other turning member, right? So if it is connecting one sliding member, so this would be applicable for slider climb mechanism. This is a sliding member and this connection is a turning member, right? In this case, the sliding member's angular velocity is 0. Why? Because there is no angular velocity, right? This is only velocity. So this rubbing velocity at the pin joint is omega into R. So this omega is only of the turning member, not the sliding member. So here omega is the angular velocity algebraic sum and R is the radius of the pin, right? Okay. They are connected by a pin of some radius. Okay. So the radius of the pin is R. Right? Radius of the pin is R, and angular velocity of B is omega B, and angular velocity of A is omega A. Right? Correct. So omega B and omega A. Right. So if these two, right, according to the definition, rubbing velocity of the pin joint is equal to omega 1, that's omega A, minus omega B into R, or omega A plus omega B into R. This R is the radius of the pin joint, no problem with that. Right? If the links are moving in the same direction, that is omega A minus omega R. If they are moving in opposite direction, that is omega A plus omega B. So if they are moving in same direction, we will go for omega A minus omega B. And if they are moving in opposite direction, that is omega A plus omega B. So now you see omega B is moving anti-clockwise, right? Omega A is moving clockwise. So they are opposite direction. So now we have to add this. Right now we have to add this. If in the case this is omega B and this is omega A and this is our pin joint radius R, right? So here omega B is rotating in clockwise and omega A is rotating in clockwise. So here both are moving in same direction. Here we will go for omega A minus omega B for the same direction, right? If they are moving in same direction, that is omega A minus omega B. They can either be rotating in clockwise direction or both may be rotating in the anti-clockwise direction, right? Like this. It is same direction, omega A minus omega B, it is opposite direction, omega A plus omega B. Either they can move towards each other or they can move on the other way also. If this is omega B and this is omega A also, that is opposite direction, and we will go for omega A plus omega B into R. This radius is the radius of the pin joint, right? This is the radius of the pin joint, right? So this is what called as the rubbing velocity, right? Rubbing velocity. Rubbing means, you know, right? A kind of friction. So when these two links are moving, there could be a kind of friction, right? So in order to find the rubbing velocity, we use this equation. And this is for both the turning members, right? You know what is a turning link and what is a sliding link. So if based on a point, it is kind of making a rotational motion, that is turning member. If based on a point, it is moving backward and forward, that is sliding motion. So in this case, say for example, it's a kind of spiral drive mechanism, right? So here, this is turning member, right? Based on this, this is going to turn. But this one is a sliding member. This is going to go only backward and forward. Here, this is the turning member, and this is a sliding member. When we come across to such situation, we don't consider the angular velocity of this sliding member since it does not have any angular velocity. If it is moving in an angle only, it will have an angular velocity, right? So this is not moving in an angle, this is moving in a straight line. So which will not have any angular velocity, right? So in that case, we will consider only the turning member, the angular velocity of that into the radius of the pin, right? So this will give you the rubbing velocity of the system, right? This mechanism. So if both are turning members, then you will have algebraic sum of the members into the radius of the pin. If it is a sliding member and a turning member, then you will have only the angular velocity of the turning member into the radius of the pin, right? So this is all what about the rubbing velocity, right? So now we will go for a question, right, on how to find the relative velocity. In a 4-bar chain, A, B, C, D, right? So there's a 4-bar chain. AD is fixed and is 150 millimeter length. The crank AB is 40 millimeter long and rotates at 120 r.p.m. Right? And direction is also given clockwise. While the link CD is equal to 80 millimeter oscillates about D, BC and area of equal length, find the angular velocity of link CD when angle BAD is equal to 60. Right? So this is our question. So according to the question, in a 4-bar chain, right? So we know that's a 4-bar chain. AD is fixed and this 150 millimeter long. Okay, so I'll just here 150 millimeter. So this should be drawn according to the scale. So that's why I have a ruler here, right? Since I'm not using it even, but we need to have a scale factor, right? So 150 millimeter, I will draw like 45, right? No, 50. Okay. So I'll draw 150 millimeter as 50 centimeter, right? So I will write a scale factor 150 millimeter denoted by 50 centimeter. Since my board is very big, I am going for a big picture. But when you are drawing in your papers and copies, you may have to go for a smaller scale factor, right? That's fine. So now this is AD, right? AD is 6. AD is 6. So 150 millimeters, so that is 50 centimeter according to my scale. You don't have to write this, but you need to write the scale factor. So this is known as scale factor. Alright. Radius piston is 150 millimeter long. That's done. Crank AB is 40 millimeter long and rotate at 120 rpm. Right. So A. Now I have a crank. Right. That is AB. So according to my scale, 150 millimeter denotes 50 centimeter, which means 40 millimeter is equal to how much? 40 by 3 centimeter. So I will go for 13.3 centimeters, right? So 13.3 centimeter, something like this, right? So I don't know the direction now, right? But it is still given in the question. Find the angular velocity of the link CD when angle BAD is 60, right? So somewhere B, this is going to be B, A, D is 60, right? BAD is 60. So DA, now I have to go for a 60-degree angle to denote the B, right? So better you use a protector to find the 60-degree angle, but I mean, we can find by this also, right? Just by simply drawing an arc. Since it is 60 centimeter, I can make it, right? I'll draw an arc. Okay. So only for 60 degree this is applicable. By drawing an arc, you can find the direction. So if I join this point, right? So this angle would be 60 degree. Right? Okay. You know how to draw a 60-degree angle, right? You take an arc, right? I mean, you draw a line, just draw a line, right? Say for example 10 centimeter, right? You take your arc, right? And make a curvature over here, right? From this point, you make a curve over here, right? From this point, you make a curve over here, right? You join these two, this will give you your 60 degree, right? So in order to find your 30 degree, you take these 2 points, right? From this point, you draw an arc here. From this point also, you are draw an arc here, right? Like this, like that. You join these two. This will give you your 30 degree, right? So like this, you can draw. But since we are measuring and finding the answer, the better way is to use a protractor exactly, right? Because instead of 60 degree, if you draw 59 degree or 62 degree, then once you move the scale factor and finding your final answer, that would vary very much, right? So now I have found the 60 degree. So this is 60 degree, and now my length should be 40 by 3, that is 13.3 centimeters, right? So that's how it's given 40 millimeters. So I will use the length scale, I will marker, right? So this is the point B, right? This is point B. So angle B, A, B is 60 degree, right? And AB is 40 degree. Okay. And this is rotating at 120 rpm. Right? This is rotating at 120 rpm. So omega equal to 120. 120. Omega is equal to 120 rpm. Right? And clockwise, right? So moving this way, clockwise. While the length CD is equal to 80 millimeter, right? So A, B, D is here, so C must be somewhere here, right? So the length of link CD is 80 millimeter and it is oscillating about D. So it is going to oscillate about D, right? Something like this, it's going to oscillate, right? So if CD is equal to 80 millimeter, according to my scale, how much would it be? 80 by 3, right? 80 by 3. 150 by 3 is 50, 40 by 3 is 40 by 3 centimeters. So, and 80 by 3. 80 by 3, how much? It should be 26, right? So now, I will draw an arc of 26 centimeters. Right? I don't know the direction of this one now. Right? I don't know the direction. So what I will do, I will draw an arc of 26 centimeters, right? 26 centimeters. I will draw an arc. Okay, so this might not be perfect, but when you are drawing, right, make a kind of perfect. Okay? Right. So somewhere on this arc, the C is going to be, but I don't know where. And one more data is given, I didn't use it yet. BC and AD are of equal length. AD and BC are of equal length. So you know AD is 50 centimeter. Right, 150 millimeter according to my scale, that is 50 centimeter. So this BC is also going to be 150 millimeter, and according to scale factor, that is going to be 50 centimeter. Right. So I need to draw an arc of 50 centimeter. I don't have 50 centimeter here. Right. So I'll draw some arbitrary arc. Right. So I will make another arc of 150 millimeter from here, not from here, from here. From BC 150 millimeter, I will make an arc. Okay, so this 80 millimeter arc from B and 100 millimeter arc from B is going to meet at a point. Right, so now I have my point C here. Right, C. So BC according to data it is given 150 millimeter. So that is according to my scale that is 50 centimeter. Right. And this BC according to data that is 50 millimeter. According to my scale that is 26.6 centimeter. Okay. So this scale factor you don't need to write it and everywhere, right? Simply mention here is fine. This is the scale factor, but for your easiness, I'm writing it, right? I will erase this. Now you know, right? So this is the diagram, right? This is our 4-bar shape, right? So now I will erase all these arcs and all. Then only this will look like me. Okay, this is our final 4-bar shape. Now we see the question. Find the angular velocity of link CD. Link CD. So I need to find the angular velocity of CD, right? When the angle BAD is 60, right? When the angle BAD is 60, right? This is relative velocity method, right? Now we will use the given data. Data one is omega is equal to 120 r.p.m, right? Not omega. N, that is equal to 120 r.p.m. So I can convert it to omega. Omega is 120, N is 120, right? 2 pi n by 60. 2 pi n by 60, that is equal to 2 pi into 120 by 60. So that will give you around 12 points or something. Yeah, 12.68 rad per second. So 120 and 60 would be solved 2 into 2, 4 pi. 4 into 3.14, that is 12.68 rad per second. So omega of this AB is 12.68 rad per second. Right? Now we will draw the velocity diagram. So this diagram is known as space diagram, right? This diagram is known as space diagram. So you whatever the data given in your question, you now transfer it to the diagram. Now from this diagram, I will go for the velocity diagram, right? Since the length AB is 40, right? Therefore velocity of B with respect to A can be found, right? So I know the angular velocity of this, right? 12.68 rad per second. I know the length of AB, right? 40 millimeter. So based on these, I can find the velocity, right? Velocity of AB. You know, omega is equal to V upon R. Omega is equal to V upon R. So V is equal to omega into R, right? Omega, I know 12.68 rad per second. And R is equal to, in the question it is given 0.04 meter, right? 40 millimeter, that is 0.04 meter. So which will give you a final answer of 0.503. 0.503 meter per second, right? So now I know the velocity of this B and angular velocity of length AB, right? So B is a point which is both in the length AB and on BC, right? Now I know the velocity of point B. Or I can write it as velocity of B relative to A. In this particular case, this is going to be same. Why? This A is a fixed length, right? This is not going to move anywhere. So I don't need to mention it. I can say as like velocity of B relative to A, or I can simply say velocity of B, right? So this is done. Now I need to find the angular velocity of this CD. That's the question. Okay. Now we'll draw the velocity diagram. You know, the velocity diagram or velocities need to be drawn perpendicular to the link, right? Perpendicular to the link. So this is AB, okay? Perpendicular to this means this way, right? And the magnitude is 0.503. Now I need to go for a scale factor again to denote this thing, right? So it needs not to be same as that one, right? You can take another scale. Okay. So instead of 0.503 meter per second, I can say like that is 50.33 meter, right? I can say, right? So that is perpendicular to this direction. So I will draw that diagram. Okay. So parallel to this, right? Very parallel to this, you need to draw another line, right? Like this. Okay. This and this should be parallel. So for that, in your papers, you need to use a roller scale, right? Take this one, move it, and draw, right? That is your velocity of B, right? Velocity of B. And I am taking a scale of 0.503 meter per second as I'd say like 5 centimeters. This is not 5 centimeters. That's what I'm saying for a scale factor, right? So now I move this one here, right? And this should be parallel to this, and there should be a scale factor, right? So this I will mark A is a fixed point to B, right? A is a fixed point, all right? B is also a fixed point, right? So B is also going to be the same point, right? And now I will draw for the CD, right? So that is again going to be perpendicular to CD, right? So D is a fixed point, CD is in this direction, right? So I don't know the magnitude, right? I don't know the magnitude. I know only the direction. So parallel to this, right? Parallel to this, I will draw another line. Okay. This line and this line should be parallel. I don't know the length, so I'll just draw it. Once I draw this line also, let us see how to join that particular point, right? So this is perpendicular, and it is from D to C, right? D is a fixed point, D to C. All right. We don't know where the C is. Now we will draw for the CB, right? CB is a link, and the velocity is going to be perpendicular, right? This is going to be in some this direction, right? From B perpendicular, right? So parallel to this direction, I will draw a line here. Okay, these two should be parallel, right? These two should be parallel. So once I draw this parallel line and this parallel line will meet at a point. And that point is our C, right? That is the C point. Alright. So this is parallel to this. Alright. This is parallel to this, and this is parallel to this. Only the magnitude of this AB is known, right? That is 5 centimeter, right? So here you can directly write your scale factor, that is 5 centimeter. I don't know the magnitude of this, and I don't know the magnitude of this. Now I need to find, right? So what I can do is, I can simply take the scales and measure it, right? So you will get a value according to the scale factor. So this, say for example, 0.503 meter, you mark it as 5 centimeter. Then you will measure this, you will have a value, right? So that AC into your scale factor will give you the velocity of this AC. Sorry, not AC, DC, right? Similar way, the length of this one, right, you measure with your scale into this scale factor, right, into this scale factor will give you the velocity of BC, right? This is how we will find the velocity. So you measure it, multiply with the scale factor, and write the velocity. That's the velocity, right? So now we'll see what is the velocities already done. So I'll share the screen. So I have the space diagram here, right? Parallel to this one, there is BB. I have a BB here. Parallel to this one, there is DC, right? OCD. I have a velocity for this, and parallel to this, I have this BCD here, right? And for this BC, that is going this way, okay? Parallel to this one, I have BCD here, right? So this will give you the velocity of C respect to B, right? Velocity of C respect to B, and velocity of C respect to D, right? This will give you only the velocity, right? From this one, you need to find the angular velocity. So how to find that? Omega is equal to V upon R. So once you get the velocity here, you will divide it with the length, right? You will divide it with the length, and you will have the answer of angular velocity, right? Now we'll see how to find it. Right? Since the link AD is fixed, right? Now we'll see how to draw that, right? Since the link AD is fixed, therefore points A and D are taken as 1 point, right? Because they are fixed in the velocity diagram, right? As I told you. Draw vector AB perpendicular to BA. So velocity vector is always going to be perpendicular to the link, right? So some suitable scale. So you need to take the scale according to your space in the paper, right? You can't go for another paper, right? To some sort of scales to represent the velocity of B with respect to A, or simply velocity B. It's A is a fixed point. Now from point B, right? From point B, draw a vector BC perpendicular to CB, right? Start from where you know the direction and the magnitude, right? You have to start from where you have the direction and the magnitude. So on the AB, you have both direction and magnitude. So once you draw this scale, right, when you measure it, you will have BC is equal to BCD, that is 0.385 meter. CD is equal to 0.385 meter. So you need to measure it, and when you convert it to your scale factor, you will have BCD is equal to 0.385 meter per second. So when I measure this, CD and multiplied with the scale factor, I have VCD, that is CD into scale factor, which is giving me 0.385 meter per second. Right? From this 0.385 second per meter per second, I need to find the angular velocity. Right? That's the question. So angular velocity omega is equal to V upon R. Right? V is equal to 0.385 meter per second upon R. CD. Right? This is CD. 80 millimeter. That means 0.08 meter. 0.08 meter, which will give me 4.8 rad per second. 4.8 rad per second. Right? So this is our final answer. You can see the screen, right? Okay. Right? So that will give me 4.8 rad per second. Okay. The crank and the connecting rod of a theoretical steam engine are 0.5 meter and 2 meter long respectively. Right? So now we have the length of the crank and the length of the connecting rod. The crank makes 180 rpm in the clockwise direction when it has turned 45 degrees from the inner dead center position. Right? So 180 rpm in clockwise direction. So now the omega of crank is given, rpm is given, n is given. When it has turned 45 degrees from the inner dead center, right? The angle is also given. Determine the velocity of the piston, right? So now piston is a sliding member, remember it. Angular velocity of the connecting rod, velocity of a point E on the connecting rod 1.5 meter from the gudgeon pin, right? So this is an arbitrary point. And velocities of rubbing at the pins of the crankshaft, crank, and crosshead. When the diameters of the pins are 50, 60, and 30, so diameters are given, you have to find the velocity of the rubbing. Position at linear velocity of any point G on the connecting rod which has the least velocity related to crankshaft. So these are the questions. Right? Now we'll see how to find the answer. Right? So we need to draw the diagram first, right? So according to the given data, my crank length is given, connecting rod length is given, angle of what I have to find is also given. Right? So I will draw those data into picture. So my crank, that is 0.5 meter. Connecting rod, that is 2 meter. Okay, and I have a piston here. Alright, and when this is making an angle 45 degree, the clockwise n is equal to, this is your inner dead center and that is your outer dead center. From the inner dead center, it is making an angle 45. Right. Now, question is, we need to find the velocity of the piston. Right, that's the first question. So again, we need to go for the velocity diagram. Right. First, I will go with the data. N is equal to 180. So if n is equal to 180, I can find the omega. Omega is equal to 2 pi 180 by 60. So that will give me 6 pi. Right, 6 pi is equal to 18.82 meter per second. 18.82 per second. Okay. So omega of crank is found. I know the length of the crank, that is 0.5 meter. From this data, I can find the velocity of point on the crank, right? So I will write it as B, O, B, and what are the other points given? E is given, right? E, and another arbitrary point, E, which is 1.5 meter from distance. Okay, these are points are given. So if my angular velocity is equal to 18.82 rad per second, 9.426 meter per second, right? So velocity of B is equal to O, right? Velocity of B is equal to O. know the velocity of v with respect to O now. Now I can start the velocity diagram, right? Angular velocity of connecting rod. That's the question, right? That's the question, right? So velocity. Okay, we'll go one by one. From the velocity diagram, we need to find the, we need to find the BEM by measurement, right? So now we need a suitable scale, right? So 0.5 meter, here 2 meter is there. I will go for a particular scale factor, right? You need it, right? Only thing is you need to mention what your scale factor is, right? What is your scale factor is. So I'll draw, okay? O is the big point, right? From O to B, so the velocity is going to be in a particular direction like this, right? It will be like this. So parallel to that, I will go from B, O, right? O to B. This and these are parallel to each other, right? These two are parallel to each other. I know the velocity, that is 9.426 meter per second, right? So I will put it into a scale factor, right? Don't forget the scale factor. Say for example 9.426 meter per second, you are taking as 9.426 centimeter. This is an example. You don't have to exactly stick with that, right? Either you can multiply it with 2 and go for like 19 point something, or you can divide it by 2 and you can go for like 4.7 something, right? That's up to you. I'm just taking it for a scale factor. You need a scale factor. That's the point here, right? So OB is marked. What else we can do is we can go for the piston. We know it is going to move either this way or that way, right? Either this way or this way because that's the motion of the piston, right? So that's easy for me. So I will go for that second, right? It is going to make a motion only in this direction, which means I know the direction, but I don't know the magnitude, right? So I will go and I will mention it as VP, but I don't know where the P is. Somewhere here it must be. I don't know where it is, right? And this is B. This I know with the magnitude and direction, right? Velocity of B with respect to O, I know the magnitude and the direction. Now I have a connecting rod, right? Connecting rod. So connecting rod, which is making an angle like this, right? So this is connecting rod. Perpendicular to that, it is going to make a angle like this, right? So parallel to this, I am going to draw something here. Okay. So now I have completed my velocity diagram, right? So this line of motion of P and this line of motion of connecting rod, the velocities, they will meet at a point, and that point is our P, right? That's our P, right? So my O is there, B is there, P is there, right? All 3 points are there. So based on this, now we can find the angular velocities and the velocities. Okay. So angular velocity of connecting rod, we can say from the velocity diagram, we find the velocity of P with respect to V, VPB. So what you have to do is measure it, right? So this is respect to the connecting rod, right? PB perpendicular is this, that is this. So your measurement of this is going to give you the velocity of the connecting rod, velocity of PB, right? And right here connecting rod, right? So when you measure it, right, according to, then you have to measure it and multiply it with scale factor. Right? So you will have a then PB into scale factor, which will give you the velocity of PB, right? So according to that, velocity of PB is coming as 6.8 meter per second, right? So velocity of PB is coming as 6.8 meter per second, right? So I know the velocity of PB here now. The question is distance velocity. So now I have to move from here to the distance. First, I will go for the angular velocity of this one, right? So angular velocity of PB equal to velocity of PB, right? That is this 6.8. Omega is equal to E upon R, right? Omega is equal to E upon R. 6.8 meter per second. Divided by R is the length. Length of the connecting rod is 2 meters, right? 2 meters. I will have 3.4 that per second, right? You can see my board, right? Yeah. So 3.8, 3.4 that per second. Right? So now I have found the velocity of PV and this is known and this is known, right? Okay, you measure this one, OP, right? You measure this OP and you find the velocity of this, do the same, divide it with the length, but that is not asking the question, so we don't go for that. Right? Then our third question is velocity of point E on the connecting rod 1.5 meter from the gadget pin, right? Velocity of E on the connecting rod 1.5 meter from the gadget pin, right? I will mark the point E over there. Right? I will mark E over there. Once I mark the E, I will mark that particular E on the velocity diagram also. Right? I need to mark, right? So if I have PB as 2 meter and PE as 1.5 meter, that is 4 is to 3 ratio, right? PB 2 meter, PE 1.5 meter, that is 4 is to 3. So similarly, I will go for there also. PB, if I take this as 4 units, I will go for PE, right? From P to E, yeah? From P to E, 3 factors, 3 fraction of the 4. So from P to towards B, E is there somewhere 4 is to 3. So if I consider this as 4 units, right? So that is 6.8 meter per second, that is right. Then this must be the 4/3 of the total length, right? 4/3 of the length we have the E here, right? So this is how we mark any arbitrary point on a length in the velocity diagram. Find the velocity of that particular point, right? Now I will join. I will join this. Now we can find the velocity of this. Velocity of point E on the connecting rod 1.5 meter from gadget pin, right? That is 1.5 meter from the gadget pin. That is BE vector, right? That is BE vector. Again, we need to measure it, right? So here is our BE vector. So what I have to do, I have to measure this then, right? That is OE. That's the right. So velocity of E is equal to then OE. So your get factor, you will have the some value, right? So to do it, you will have velocity of E is equal to 8.5 meter per second, right? You measure this, multiply with your scale factor, right? Then the next question is uh, position of this point G, right? Position of any point G on the connecting rod, right? So again, it's related to the connecting rod. On any point G on the connecting rod, which has the least velocity related to crankshaft. Right? So now we have to go for the least velocity, right? So this is again related to the connecting rod, that is PB. So now I have to do something with this length, right? I need to mark first where the G is, right? So it's only said which point will have the least velocity, right? So I need to mark that particular point. I don't know where will it be, right? You know, from a point to any arbitrary line, right? From a point to any arbitrary line, the minimum distance is the perpendicular of that line to the point. So if this is my point A, and this is the line OJ, okay? And if I need to find the minimum length between this OJ and A, the minimum length is the perpendicular drawn from this O sort of A to OJ, right? Perpendicular drawn from A to OJ. This is will give you the minimum length. So whatever the line you are drawing beside that would be lengthier than this line. Right? This is the minimum length, right? So we will there, right? So this is my VP, right? This is my VP. From here, whatever the line which is giving me the minimum length should be the perpendicular from this point to this point, right? So I will mark it, right? So when you are drawing in a copy, you take the square, right? Triangle square, and you find the perpendicular, or you use a protractor to find the 90-degree, right? From this to this, right? So for your understanding, you need to do that because small difference in the angle will have a big effect on the length. So when you multiply it with your scale factor, that will even be magnified, right? When your final answer would be very different from the expected answer, right? So when you are marking the angles and finding the angle, be very specific, right? So say for example, this is my not example. So this is my perpendicular. So this should be the minimum length, right? This should be the minimum length. This line and this point, they are joined with a line, and that line is the perpendicular of this line off from this point, okay? And this should be the minimum length now. So the least velocity is associated with this line, right? So by measurement, we can find Bg, right? That is 5 meter per second, right? So from the BP perpendicular to O, right? We will have the vector OG, right? OG, okay? And I know I can measure whether I need this or this. I can measure, right? By measurement, we find that vector Bg is 5 meter per second, right? Vector Bg is 5 meter per second. So you need to measure it and multiply it with the scale factor, okay? So I am simply saying measurement, you measure it and multiply it with the scale factor to get your final velocity, right? The position of point G on the connecting rod is obtained as follows, right? The question is asked, mark that point, where the point is. So I now mark it in the velocity diagram. Now I have to mark it in the space diagram because question is asked, mark that particular point, right? So if I know this is 5 meter per second, right? I can measure this one. No, this one doesn't matter. Only thing is we are going to transfer this from here to here, right? So we'll go for the ratio, right? So Bg upon Bp, right? I'll write Bg upon Bp is equal to, right? Bg upon Bp is equal to, here I am going to transfer it again, Bg upon Bp, right? I don't know where the G is, right? Bg upon Bp. I don't know where this G is, but I know Bg, right? Bg I can find 5 meter per second, okay? And BP I have already found. Where's BP? That is 6.8 meter per second equal to BG. That I don't know. I have to mark, right? Into, so that is I will put X upon BP. BP I know that is 2 meter, right? BP is 2 meter. All right. From this I can find X. X is equal to 2 by 10 upon 6.8. That will give you 1.47 meter. 1.47 there, right? So this is 1.47 1.47 meter, right? Only thing is, we need to see from where that is 1.47 meter. From P it is 1.47, or from P that is 1.47, we need to see, right? So the length is BP, right? So that is BP, from B to P. So from here it is 1.47 meter. From here that is 1.47 meter. So this is why naming, measurement, angles, scale factor, everything is very important here, right? If you take from here to there, that is wrong, right? According to naming, that is BP, from B to P, right? From B, 1.47 meter towards P, the length is, right? So that is 1.47 meter from here to here, right? By measurement, we find the linear velocity of point P, that is Vg, vector OG, that is 8, right? So we now can find the velocity of this, that is measurement of OG into the scale factor, right? So OG into my scale factor will give you the velocity of this point G, right? That's the minimum velocity. That's equal to 8 meter per second, right? If you want to make it from velocity to angular velocity, you just have to divide it with the length, right? That is dg, that is 1.47 meter, right? So 8 by 1.47, you will get the angular velocity. Since it is not asked, I'm not finding it, right? And this is the angular velocity, not velocity of the point, which has the least velocity on the connecting rod, right? Velocity of the point, any point, right? I don't know where the point is on the connecting rod, which has the least velocity related to crankshaft, right? Read the question, relative to crankshaft. So from here, crankshaft to that point, right? The previous case, the point E, right? We were discussing about the point E. That one, the question is given from the gudgeon pin, the point E is 1.5 meter, right? So gudgeon pin is here. From gudgeon pin, the point E is 1.5 meter. This question is from crankshaft, the point G is 1.47 meter, right? We need to pay care on that. From where we are measuring, right? That's what this relative velocity based on which point we are measuring the other object, right? And now the final question is velocities of rubbing at the pins on the crankshaft, crank, and crosshead, right? Crankshaft, right? Crank, and crosshead. Uh, when the diameters of their pins are 50, 60, and 30 respectively, right? 50, 60, and 30 respectively. So I know this is a sliding member, right? This is a turning member. So here, both the omegas are going to come, right? This is a sliding member and this is the turning member. So only the turning member is going to come. This is a fixed thing and this is the turning member. So only one omega is going to come, right? So based on that, I will go for that, right? So first we will go for the velocity, I mean rubbing velocity at the point of crankshaft, right? Pin of crankshaft. So here is the pin of crankshaft, right? This is the fixed link and this is the turning link. So there is only one angular velocity, right? So this angular velocity I have already found, VB omega OB, right? Omega OB is 18.82 rad per second, right? And the diameter is given, that is 50 millimeter, right? So rubbing velocity, and like just RB, right? Rubbing velocity is equal to omega into diameter, right? Right? Omega into diameter. So that is equal to 18.82, right? That's the omega of the crank. 18.82 into R, that is given as CO is 50 millimeter, that is 0.05 meter. 0.05 meter. That will give you, if you multiply 0.4 ground meter. Right? So rubbing velocity of crankshaft is 0.47 meter. Right? And now the rubbing velocity of the link, right? This link. Okay. So here this is a turning member. This is again a turning member, right? So when this moves that way, right? This is going to move that way, right? So this is going to be opposite. So I will write addition of this plus that. So here this is 18.82 and EB already found, right? 3.4, right? EB is 3.4 and this is given 18.82. So 18.82 plus 3.4, put the unit into the radius of the pin, diameter of the pin. Diameter of the pin is given 60, right? Which means I have to go for radius, that is 60 by 2, 0.06 by 2, 0.05 by 2. Okay. So if I solve it, I will have 0.667. 0.7. Okay. Third category is the slider, right? So here I have a turning pair and the sliding pair. So now this sliding is going to be 0, only turning is going to come in the action, right? So the radius is given 0.03 meter is the diameter. So I will go for 3.4 rad per second to 0.03 by 2. The diameter is given. I have to go for the radius, right? So which will give you 0.051. 0.051 meter per second, right? So this is the rubbing velocity of point P, 0.051. Rubbing velocity of point B, that is 0.667, and rubbing velocity of point 4, which is 0.47 meter per second.